Hello. Hello. Volume check. Or should it be like audio check? Audio check. Yes. Audio. Okay. Just a quick documentation on my cycloidal drive designs because I'm cleaning out data from my Fusion workspace now, and I just realized like I have so many versions of the cycloidal drive designs, and I'm going to delete them, but I think it's a bit sad to delete them. Like this is how I learn things. So I think I can just document it. Oh my god, I didn't share the screen. Oh, okay, now you can see it. So like tons of deprecated cycloidal drive designs. Oh yeah, just these. So I think it may be worth to just do a short documentation on them, and perhaps there could be some points helpful for the viewers and also myself in the future. I think this one is the first version, cycloidal drive standard. So I think all of these are generated with the this fancy tool like cycloidal drive maker. It's pretty useful. Like you can just input the numbers up too large. You can just like change the numbers and it will even have a preview for you. But the bad thing about that is like after you generate the design, like after it's generated into this actual 3D file, you cannot change the parameters. So and that's um, very annoying, I guess. So yeah, like this is it will only appear on the version history as a single marker, and like you cannot edit it. Edit feature, it won't work. Yeah. So yeah, that's why I have like this many versions of the cycloidal drive files, because like I cannot change it. And like for example, if I decide to change the thickness of the cycloidal drive cycloidal disk, then I need to make a new version and redo all the steps. So that's very annoying. On the up-to-date version, I'm using a script of my own, like this one, to just generate the sketch. So I can just edit the sketch or even like recreate one if I want to have a new one. So yeah. So like these are generated by this like cycloidal drive maker. So it will like automatically give you like these parts, and I think I have a bunch more. I don't know why. Okay, I didn't even draw the. Okay, so there's motor hub, but I didn't draw the other parts that holds the motor. Yeah. I'm not sure which one comes first, actually. I think this is the first one. Okay, never mind. This should be the first one. This is so in the basic form. Yeah, so like for these small ones, I was designing for the elbow joint. So it uses a small like 5010 BLDC motor. So the diameter of the housing is then like 72 millimeter. Yeah. So this is the first version. Oh, I don't think this is the first version. So I have a few like scratch version just to like make sure that my tolerance and all those stuff works. And this is actually the first like formal version. So I like I have tried to design two formats of each actuator. So one is like the housing is attached to the motor housing, and like these stays as one part, and the output shaft is this space which rotates, and the other one is the opposite. Like, okay, this is very raw form. The other one is like we attach the output shaft with the motor housing, and it's the housing that it's rotating, and it's the output end. Yeah, so this will be very useful for connecting, like for example, you have parts just like the elbow position. So you have two rods joining together, and you don't want something stick in the front to drive parts. Yeah. So this makes sense, and the difference is only like the gear ratio is off by 1. So for example, for this version A, the output is on the front, the reduction ratio is 15:1, and for the other one it's 16:1. So off by 1 Ts. Yeah, so this is the first one. I don't think I have anything to talk about. This is very crude form. Maybe this one? Yeah, the input shaft. Okay, I have already changed this one. That's brilliant. So yeah, the input shaft keeps snapping. So originally there was not this block. It's only the hex shaft, and then like it gets rounded pretty quickly. Like immediately after putting some load, it becomes a round rod, and it just starts to rotate within the input shaft of this one, the cycloidal generator. So then I add this like square thing here, which acts like a key to the shaft, and that helps a lot. So I'm using this design like moving forward. Yeah. And also I was hesitated about how to put stuff together. Like this is one solution. Like I have the motor hub here, and I have the generator here, and they need to be two parts because like there is a bearing here and there's a larger piece here, so you cannot really put the bearings through to the middle. And another way to do it is like you have this part fixed to this part, and like the mounting point is between these two. But then I think like these will have different loads, and I'm not sure like what it will look like if there's any negative effects. So yeah, and another method is to make this one larger, because like the eccentricity here is, I think it's oh my god. Oh my god. Oh, okay. Oh yeah, that makes sense. The eccentricity is 1.5, so it's 3mm difference here. So we just need to make this one 3mm larger, or I guess 6mm larger. Yeah, but then we will have two different cycloidal discs, and one of them will look like, okay, offset face. Where is offset face? Will look like this, and this clearly doesn't work. So yeah, it doesn't work. We can, okay, what's the diameter of this thing? It's 8mm. We can also make it smaller. So the bearing I have, there's a 12 by 8 by 3.5, and there's also a 10 by 6 by 3. So we can make it 2mm smaller. That actually can be a good idea. Yeah, that is actually a good idea. I can try that in the next revision. Yeah, or we can like make. Okay, let's see. So this one is 8. So increased by 6, we got 14. 14 inner diameter. Okay, I have 18 by 12 by 4, so that's not enough. But if we decrease the eccentricity to 1, we only need to, the difference will become like 2 millimeters. So 8 millimeters plus 4, we got 12, which works. Okay, we can try that, but then the diameter of the outer is becoming 18, so here's 12. 18 we need to offset by how much? By 3. Okay, it still like looks like this. But if we decrease the eccentricity, this thing will be smaller. So I think that actually works. That actually works. Only, okay, that works. I was going to say like there's a 0.5 millimeter difference in thickness of the two different sized bearings, but we can make that 0.5 be the gap between these two discs. So like this face will press against the bearing, or like be aligned with the bearing, but the bearing will extend here, and then it's the other one. Oh my god, it actually works. Okay, it actually works. How about the, okay, I need to check. I need to check one thing really quickly. Eccentricity. Okay, the larger one is using eccentricity 2, so I don't think eccentricity 1 will be very sufficient. Okay, let's try to generate the profile. So here we want 1 instead, and let's run the script. Oh my god, that won't work. That's too thin. Like here it's too small. That won't work. Okay, but if we go on the smaller side, we have MR106. MR106. That will be the MR106. Okay, where's my file? It's disappearing. Oh, here. 106. So this one will be decreased to 10. And this one will be decreased to 6. It's 8 now. Decreased to 6. And the other one, the inner diameter is 8. 8 minus 6, it's 2. So we still have eccentricity of 1. Annoying. Wait. Okay, I cannot do math. So if we got a 8 here, and we got a 12 here, to make them like this, and also on the same line. What's the difference here? It's 2, right? It is 2. Okay, problem solved. We can do 2. Okay, no, it's still 1 as eccentricity. Yeah, this will be the pattern, which won't work. Okay, I'm using this website. Yeah. I forgot. 68 series, 6800 should be the thinnest one, but it's too large, right? Oh, it's fine. Okay, width is 5. How about 6, 7? Width is 4. Okay, so 6, 7. The another ink. This is too large. Oh my god. Why this is still so hard? Okay, this won't work. This won't work. Another thing we can do is, like, if this is 4, we can just cut it here. But that will be very ugly and dangerous and not secured. Well, it depends. It depends. How about 3? So 1.5 eccentricity. This looks ugly. So ugly. Okay, so 4. If we do 4, we can cut a piece like this and insert this thing later on. Okay, no. This won't work. This won't work. I'm giving up. We just need to find a way to, like, this is too ugly. We just need to find a way to make this cute thing stronger, which we can. And it's actually pretty easy. We can just replace the thing with a steel one, like hex steel rod. It's pretty easy to find, like this, just smaller one. Like what's the size here? That's 4. Yeah, like anything. Okay, this is M4, but like, yeah, it's easy to find. It's easy to find. 4 looks this large. It's just hard to find the small, short ones, but like we can cut it. Yeah, this won't be a problem. Sticking to this plan. Also, this makes changing the motor easy. We can just pull it out. Yeah, this is a solid choice. Yeah, so basically this is version 1. Okay, and I think this one is version 2 or the opposite, I forgot. Maybe this is the version 1. Yeah, I think this is the version 1. So I finished this one and I finished this one. Yeah. And then I proceed to the previous, like the standard one. But I got, like, there's something interrupting and I then changed it to the final one, which is this one. And then I got to the ultimate one, which is the ultimate one. The ultimate one. Yeah, this is the one okay, this is the second to last version. Yeah. It's pretty finalized. I even forgot like which part I changed which part following this one. But yeah, I got 2 versions. This is the second version. Oh, okay, it doesn't have the output shaft, the output block, but yeah. So this is ultimate. This is final. I even draw a motor for it. Like how beautiful this is. Like even have the decal on it. Yeah. And I think I did a motion study for one version. I forgot which one, or perhaps I didn't save it. Okay, maybe I didn't. Analysis, what's this? Okay, this section analysis, yeah. So one tricky part is like for version A, it's all fine. Like it's all fine. We got a bearing here and we got a bearing here. And the motor can be pretty close here. Where's the motor? We don't have the motor on this version. Oh, not standard, final I mean. Analysis. Yep. We got the motor here. So the clearance is the clearance is pretty good. Okay, so for this version, the limiting factor is this screw here because I wanted to hold it in position, and also I wanted to have some thickness to screw, like to hold the plating. I can actually make it a bit thinner, but yeah, and also this part is the limiting factor because the motor has a rod extruding from here. Yeah, and that's very inconvenient. So yeah, this is the like close to the thinness it can be, but which is fine, and yeah, it's fine. But for output B, it's pretty stretch here, and it's like even this is fine on the smaller version, but on larger version, where is my larger version? This is smaller version. This is the larger version. So if we create a section analysis, so this is type A, looks fine. We can, like, this is like a huge room here. But for type B, here, that's the limiting factor. Yeah, that's why, like, for type A, it's so a huge empty room here, because we need to account for also type B. So on the next upcoming version, yes, I'm yet again trying to draw a new version. I decide to cancel type B and just keep the type A format. And this way we can shrink the type A by a lot. Yeah, it's a lot. How thick is this one? Oh. Wait, section analysis, okay. this to this, 8 millimeters. We can make it 2. So 6 millimeter decrease. How about this? This 2. Oh my god. Okay. That. This. Yeah, to this face. It's 9. Okay, 9 millimeter. We can make it 2. So 9, that's 7 change. 6. Let's just make it 6 to be safe. Like 6 millimeter. We can just move this thing by itself, like to here. And then we can have the space to account for like motor driver stuff. So we actually can have an integrated motor actuator. Yeah. And also I'm trying to decrease the room here. Like this is also another huge block of wasted room. Yeah. Annoying. Pretty annoying. And also if we can somehow find a thinner bearing for this one, it can be further decreased. Okay, but the limiting factor is the teeth here, because we need something to press against the bearing. So yeah, we cannot change this much. Yeah, but like it just reminded me that like this smaller one doesn't have the problem of shrinking space down, because like the motor is the issue. The motor is the issue, because the small motor is slant head. Like this is wasted space here, like a full, how much? A full 6 millimeter wasted space. So sad. And also here, oh my god, what is this doing? Another 7 millimeter. That's 10 millimeter. We could have made this thing like 10 millimeter thinner. Yeah. If we change this one to type A, do we have some space to spare? Yes, we do. Yes, we do. Okay, so this is the limiting factor. Yeah, never mind. We don't. Annoying. Mad motor. Mad motor, why do you have this ugly looking stuff? Multi-rotor, yeah. Yeah, like these, they all have this wasted space. But at least these are flat. These are flat, like even this is fine, this is fine. Okay, I'm using this, but a thicker version. So yeah, this is fine. Okay, actually this is not fine. I'm holding the motor now, and this yet another like 8 millimeter wasted space. Oh my god. Why? But at least the bottom is flat, so that's acceptable, I guess. But for this thing, it's slanted. It's creating more unusable space. Oh my god. Okay, but it is what it is. We don't have control over that. This is thicker than, yeah, definitely thicker. Okay, another option is the T motor. But I think they're pretty similar. I don't actually know which correspond to which. I think this, yeah, this 5006. But they don't have like thicker version. .408 1005. So they don't have the 40 like I mean 5010 510 5010. Huh. Yeah, like still, it's with the space here, with the space here. Oh my god. Huh. Annoying. Annoying. But one good thing about T-Motor is that it supports, I think it supports like custom motor. This is a huge one. Oh my god. Okay, but they support custom motor, I think. Yeah, frameless motor. Yeah, just this stuff. But it's too small. Yeah. And too expensive. I wonder how can you mount this thing like to a shaft? Just glue it. There's no other way. Okay, what's the spec? Yeah, like it's 1.76 Newton meter compared to 6C12. Compared to this one, it's like okay, it didn't give out torque, but like current 36 amps at what voltage? Or like maximum power 1.7 kilowatt compared to this one. Oh my god, you don't agree with each other. What's the rated voltage? Okay, I think this is probably powerful than this one. Ah, interesting. Okay. Yeah, 2.64 Newton meter. That's double. That is doubled. Okay, not actually doubled. It can go up to 5. Huh. Short-term operation to 5 Newton meter. This is worth a try, actually. What's the diameter of this thing? I guess 1,000? 104 millimeter. Oh, that's large. That's pretty large. Yeah, so because it's an in-runner, so it loses that torque. Yeah, I don't get it. Why they want to use in-runner? Outrunning gimbal motor. This is small stuff, right? Yeah, this is small stuff. Okay, now this documentation is turning into a online shopping. R series outrunning motor. Yeah, this is too expensive. Gimbal motor. Yeah, just not optimal, not optimal. Yeah, so still back to that topic. There's wasted space. And the good looking one, the M6 series, is a bit too large to use in places like joint. Like it will be protruding out. It will look like a BJD instead of an actual human being. I guess shoulder works. Shoulder kinda works. No, it doesn't work. It's too large. Yeah, so yeah. But anyway, I think it's better to just sync the two designs. Like if we cancel the Type V on the larger motor, we might as well cancel the Type V on the smaller one. Yeah. But for larger one, we can try to fit the PCB at the back. It's doable. So for lower body, it will be integrated, but for smaller motor, there is no space. Like this is too small. Unless we use another like motor driver, IC or stuff. There's no way we can fit it here. Actually, we do, but no, that will be hard to lay out. Actually, we can. Yeah, actually we can. Let me check the PCB. Yeah, there's a ton of space. We can shrink it. We can shrink it. We can shrink it. Like at least we can do a square like about this. So it will protruding outside the round framework. No, it's better not to be. Otherwise it will interfere with the structural parts. We can try. We can try. What's the diameter of this one? It's 70. Oh, so we shrink that. That thing was like 76 or something. Yeah. Basically, as a conclusion, we have different versions of these stuff, like this cute little output block. I later find out that it's not enough, so I expanded it. And this is not relevant. Yeah, and like this design here, it's hard. It's the hardest part, but also the bearing placement, also the gap. I didn't even cover the gap. I think currently I'm using a gap of 1 millimeter. We can decrease that. Yeah, this is 2.5, but I'm not sure whether that's good or bad. Yeah, because like this one it's better to make it thick and like decrease into 0.5. I don't see if there's a huge benefit there. Yeah, and also it makes the unit weird, like you are offset by 0.5. Yeah, even this one is 1, yeah. So yeah, we can figure out a way to like solve this issue, but on the other end, like there's a screw here. Yeah, we need to make this space long enough to make the screw mount reliably. Yeah. So this is the optimum solution. Okay, so for this one, I plan to add the PCB directly on the back and just add an enclosure like this. And for places like knee joint, then there will be also a bearing here. So the enclosure needs to be a bit like strong in order to support that. But like there will be a bearing here. But most of the support will happen on this side. So there will be a thick plate here going down, and going through the motor there will be a smaller one here. Yeah. Okay. Yeah. That's it. See you. Also, see you the files. I'm